Swayam Prabha. Digital India. Educated India.
Good morning everybody and welcome again to our course on mechanical micromachining introduction. Now in the last class we have seen that there are different type of bearing we can use for making a system of a spindles here, and we have found that ceramic bearing, or we can consider the hybrid ceramic bearings, are more useful or more advantageous to use in the spindle system because they have lot of advantages compared to the steel ball bearing. And we have also seen that there are different ways to use this ceramic bearing. That means, if it is a hybrid ceramic, that means we are using ball only of a ceramic material, but still the races are made of stainless steel or some other steel materials. And we have also seen that there are bearings available which are completely made of ceramic. That means inner race, outer race, as well as balls, all are made of ceramics. So those have very more amount of advantages because they are more suitable for a very high speed applications and where the heat dissipation is a issue. So let us continue our topic further on this direction. So we have discussed about the hybrid ceramic bearings, and we have done some work about this aerostatic bearing long time before, that is aerostatic guide ways. That means what we have discussed at that time, that there are some of the ways by which we can move the component in x, y and z direction. At that time we have considered this aerostatic guide ways, but we can also make bearing also in a aerostatic way, so that we can make our system more and more frictionless and wearless. So let us discuss this thing. So now here the first thing is the electric motor with hybrid angular contact bearing. So here what we are doing, that this is mostly used for the high torque requirement. That means whatever we have discussed in the last class or the before the last class, we were discussing about the bearings where we are using ball or the cylindrical roller bearing for motion transfer, right. So it is the electrical motor we are using there, and this is the hybrid angular contact bearing. So we are using ceramic as a one of the material for balls, and then races are made of steel. And here the what is the issue here, that we can mostly go with the maximum speed of a 60,000 rpm, because here also, even though we are telling that there is a less amount of contact, but still there is a contact. So whenever there is a contact, let it be line contact or the point contact, we always get a friction, and that friction in the contact bearing will actually create a problem when we go with a rpm more than 60,000 or something like that. So what is the problem, that it will become a more problem related to thermal expansion. The thermal expansion of the spindle will occur, and because of that you may not get the required accuracy in the machining processes. And so what is the solution for that, that instead of this particular contact bearing, we can use air bearing with a air spindle. So here what is the thing, that this is one of the general view of aerospace air bearing system. So here we have to supply air so that shaft and the outer periphery should be separated by a film of air instead of a ball or any other type of media. So what is the advantages here? The advantage are that you can go with a speed of a 2 lakhs rpm. Even spindles are up to 5 lakhs rpm. It's still under research state, but somebody somewhere reported that they have already made this type of bearings, this type of spindle where it will run, it runs at a 5 lakhs rpm. But it produces very low torque here, because when you go with the extremely high rpm, at that time you have to sacrifice with the torque, but still that torque is enough to use for micro machining operation, because we know that our depth of cut is very small, and we actually go with a very low feed rate in this case, and our rpm is very high. So in this particular case, it should not be an issue that torque is very low. So we can use actually aerostatic bearing or aerostatic spindle for machining of a different kind of materials. So this is the most often used spindle for high precision machining tool, are mostly that is called aerostatic spindle. Why it is used? Because it has a high motion accuracy and capable of high rotational speed, that we have seen that you can actually, because of that air film, that you are not able to get any contact between the two relative motion surfaces, and because of that there is no wear and tear of any components, and you can go with a speed depending on the supply of air and what are the other accessories attached with the spindle. So, your requirement for a high speed rotation, high rotational speed is fulfilled by this particular aerostatic spindles. It has a lower stiffness than the oil hydrostatic spindle, because here the oil is a highly viscous. So, at that time you can actually play around the stiffness very high, but that low stiffness actually it is not an issue, but it has a very low thermal deformation than the hydrostatic bearing, hydrostatic spindle. So, here this is one of the downside of this particular spindle compared to hydrostatic, but mostly generally we do not go with the hydrostatic spindle in the high speed machining or micro machining center, because this load carrying capacity is very high in this particular case, but our case it is not the issue. So, that is why we generally go with the hydrostatic spindle for micro machining operation, right. So, it is widely used for the machine tool with a high and medium load carrying capacity, because that is where our particular micro machining field is fitting in that, because our load is not very high, but it considers the medium and the small load capacities. So, now let us see these things, that what things are there inside it. So, this is the one particular aerostatic spindle, and this tool is attached at this location, and these are the different opening by which you can actually supply the air, and then other than supply there you have to apply cooling also in some of the locations. So, you will get a different part, as well as you need a electrical connection. So, some of these things are the wires for rotating the motor, which is actually inbuilt inside this particular spindle. Right. So, this is the circulation channel or circulation passage of a air supply. So, here you can get the air is actually going up to the nose of the cutting tool holder. So, it is also possible to cool this particular thing or create a some type of sensing element here, and this remaining part is given for the air bearing, which is located at this location. So, this is you consider as a closed loop continuously, because you can see that you are not actually dispensing this air into the atmosphere. In one direction, one way you can say that this air is going inside the system and this air is going outside of the system, correct. Now, you can see that you will not find any type of ball bearing or any other type of bearing, because this bearing is a air bearing. So, instead of ball and other things, that you will get some passages here. So, through which this whatever air is coming into the system, that air will actually pass through this particular sockets or passages, and then it will actually create a uniform pressure around the shaft. Right. So, this is the passage for air. Now, you can see air is going through these particular passages, and whenever there is an opening, through this opening it will actually enter radially towards the shaft. So, this is the inside view of that, and you can see here that this is the inlet and this is the outlet, that means through which it is a vent consider, and this vent again go through this particular outer periphery, and then it will be collected through that pipe, which was shown in the few seconds before. So, this is the side view. Now, we have seen this thing long few lectures before, that it has a very high radial stiffness, because when it is going down, because now suppose your tool is located here at this location, and then you are getting a force from this direction. So, you are actually going moving in this. So, you are getting force here in this direction. So, this is the force. So, when there is a force, now you can see right now the whatever this air coming through this all has the same color, that means blue color is there. So, it has a same pressure on both the side, that is on the top side and this is on the bottom side. correct. So, it does not have so much of variation, but when it is under operation, that means you may get a radial load in the different machining operation. So, at that time what is going to happen? Right. So, now load is increasing in this direction. Now, you can see whatever area is coming from this location, it is in red color, that means here you are not getting enough area here. So, we know that pressure equal to load by area. So, here area is reducing here at that time, because of that what is happening, that your pressure is increased in this location. But when it is going down, you can see that here area is increased. So, because of the higher area, pressure equal to load by area, correct. So, now here area is, this location area is high and this location area is less. So, because of that here the pressure, now you have a large area. So, you will not get so much of pressure here, but here it is small area. So, pressure will be increased from this location. Right. So, because of that problem, what is happening, that you will get a because of that again the shaft will go to the central position, again it will try to stabilize the pressure on both the sides. Right. So, now it is coming back again this location, if it is again increasing, then pressure will again differentiate between these two part, and then again you will get the part. So, this is the top view, that means from the bottom of this cross, means it is a axial cross section here. So, here again if it is from this lower direction, your shaft is moving towards down, then your pressure will be different here. So, on the upper half there is a low pressure and lower half there is high pressure. So, whatever this red color syringe or the nozzles are showing, this will create more amount of pressure here, and here this blue color has the less pressure. So, because of this pressure difference, again your particular shaft will again be in the central position, so that you can avoid this particular pressure difference. Correct. So, this is the way actually you will get the radial stiffness, and we know that this radial stiffness is very important when you do a milling operation. Now, we have seen here that it was the radially actually aligned. So, radial stiffness was very high, and now this is about the axial stiffness, because when you want to drill something, then you are plunging your tool into the workpiece. So, it has a axial movement in this direction. So, let us see that how it will compensate for the axial movement. Now, see here right now, this is the things which is attached with the tool holder. So, this is the part of them, this is the system which is the which is coupled with the spindle system, and this air supply is coming from here, and then it is dissipated from these two direction, right. So, this is the open position where the air is actually creating film between these two system, on the spindle side and on the tool side. So, now we have to say that when this particular component moves in this side, right side or left side, depending on that it will again destabilize this particular, that means there will be a pressure difference similar to the things which we have seen just now for the radial direction. The similar thing will happen in the axial direction also, right. So, now the stool is moving down, at that time you can see that here gap is less now. So, your pressure is very high in this direction compared to this right side. So, left side pressure is higher than the right side. So, again it will stabilize, and now on, if it is moving on the right side, again pressure will be less on the right side and higher on the right side and the less on the left side. So, again it will be stabilized at the center. So, this is how it is happening. So, this way actually you can control the axial stiffness also, that means wherever there is axial loading or the radial loading variable, at that time you can compensate those things within the system without actually damaging the component of the bearing as well as spindle. correct. So, this is the way it works in this case. Now, this is the drawbar mechanism, because drawbar mechanism also you can actually see these are the two springs which will actually make sure that there is a uniform pressure when you are holding the tool or when you are releasing the tool. So, when it is pressing this particular drawbar, so this is the drawbar and this is the plunger which is pushing this part. So, when it is pushing at that time it will actually release this particular. So, this particular gripping will be expanded and then you can remove your tool from this location, right. So, this is the expansion and then you put it again and then you can release that plunger again to the original position. So, again it will grip this. So, this particular thing will be gripped with a different tooling system. And this is the motor, because we know that it is integral motor type of spindle, you do not have a external motor and passing through the belt drive. So, here this particular motor will give you a rotational motion. So, now again we have to actually measure the rotation RPM also. So, here we are they are using mostly the Hall effect sensor, because in Hall effect sensor now whenever there is open position, that means the distance between this face and this face is very large. Now, how it works? So, now this is the receiver and now suppose we make something like this, correct. So, whenever this particular portion is coming, so this portion is this one and this portion is this one, correct. So, whenever the gap between these two is less, at that time it will get a signal here. So, it is something like this is a one type of magnetic circuit and this is the iron component. So, whenever it is coming close to it, at that time you will get one signal here, and when this particular location comes, because it is moving in this direction. So, now the distance between this space and this space is more. So, you will not get a signal out of it. So, how many these type of sockets are created here in this case? So, you know then 360 you have this type of 4. So, we will get 4 signal, that means it has completed one rotation. So, similar way how fast you rotate, depending on the faster you will get the signal out of it, and then you can measure the RPM of this spindle, right. So, wherever it is going out, at the time it is creating one signal out of this, and that is the way you can measure the RPM. So, here they are not probably using any type of rotary encoder, but they are using Hall effect sensor. Right. So, this is all about aerostatic spindle. But there is still one problem in aerostatic spindle also, that is called spindle warpage. There are a lot of passages through which air is coming, and this was the shaft, correct. So, air was coming from this, right. Now, consider the when air is coming, at that time we know there was shaft was in motion, that means it was in rotational direction. So, our shaft was rotating in any of this direction or that direction. So, wherever this air is plunging or it is striking the surface was variable, that means every time it is getting a new surface here, and whatever air we are using here, this air is very cold and compressed, because we need a completely dry air and without any type of water content or something. So, mostly it is cold and compressed air is coming. So, when it is striking continuously onto the spindle, then there is what is going to happen, that depends on that this particular area will be very cold. So, these are the cold spot. If that is in the case when spindle is not in rotation condition, right. So, it is not rotating, it is in stationary condition. So, let us see that what things will happen and how this warpage will create a problem. That when the spindle is motionless for a prolonged period with a cold air impinging onto the same location. So, that is what is happening here. So, at that time what is happening, the differential contraction among the location in the spindle will takes place, causing the spindle to warp. So, because of that we know that this is the one we are, let us talk about the single only. So, our air is coming from this and this is our shaft, right. So, it is continuous, it is not rotating. So, only this particular location it is under very low temperature, rest of the thing is mostly stabilized, because whatever the temperature you are using for the system, that will be the temperature of this particular shaft, because we are not rotating it. So, here this type of points are many, because this is the one point and on 360 degree if you consider this is the right, and you are putting consider lot of points 8 or 9 points here. At that time at every point your shaft will be under this type of temperature difference, right, and remaining portion will be on the same. So, that is we are looking from this part, and if you see this particular lengthwise, then we are putting one thing here, this is the one length, this is the other way and this is the probably third way. So, this particular portion does not have temperature variation, but these are the portion where you will get the temperature variation. So, because of the large variation in the temperature at different location, what is going to happen, that your spindle will warp. Right. So, what is problem because of that? Out of roundness motion due to the bending of the spindle, because now we know that when you are making a aerostatic spindle, the dimension control is very tight. So, in this case if you continue with this particular type of things, then what is happening, that you are not getting a straight shaft, or that means you are not able to maintain the dimension of the spindle. Some of the location you will get out of roundness motion, and also you will get the localized reduction in the size of the spindle, which will alter the interior clearance and the stiffness. So, because of that, because you are localized cooling it, we are not heating localized, but we are cooling localized, and remaining portion is remaining at the system temperature. So, because of that you are getting temperature variation, and we know that thermal coefficient of expansion is different for different material, and that will play important role here, that per degree centigrade change how much is the expansion or contraction in the system. So, what should be done in this case, that suppose your idle time is very high, that means suppose you do not want to use spindle for a long time, so it is better to shut off the air supply. And if you think that your idle time is not very high, then what you can do, you can actually provide a very small amount of rotation to the spindle. So, you continue air supply, but you rotate the spindle at a low RPM even without doing any operation, that is in case of the idle time is low. So, in this both the cases what you can do, actually you can reduce the temperature gradient in the spindle, and you can reduce the warping of this particular part. So, that is the one thing we have to take care during the use of aerostatic spindle for different micro machining operation, because we know that even few micron here and there will play important role or create a lot of problems in the micro machining features, right. Now, coming to the tool retention system. Now, what is the tool retention system? That means once you hold this particular part, now we know that we have all the things, that is bearing is also there, right. So, this is the system, and this is the tool holder, and this is our tool, correct. So, now there are three locations where we need a joint, right. So, this is, let us consider this is the spindle system, this is the tool holder, and this is the tool, right. So, what things are there, right. So, this is the one joint where the tool is actually grip inside the tool holder, and tool holder is again actually inside the spindle system. Now, what is the run out of this particular thing, that also makes a problem for this particular, the how what is the precision or what is the accuracy at which you are holding this particular system. Now, if you consider that if you this particular thing is exactly concentric, that means this is the axis of the spindle. system, and then you are putting the tool holder in that. Both things are matching, but from tool holder to the tool it is not matching, then you will get run out of the tool run out. So, in this particular case there is a problem. Now, if both the things are working fine, this things is correct, but there is a problem in the tool holder which is going to fit into the spindle system, then again you will get a very large amount of tool run out. So, how accurately you are fixing this thing, that is one issue, and once you start machining operation, then again you will get a different type of forces in different directions. So, at that time how this thing will behave under dynamic condition. So, how perfectly you are gripping the system from spindle to tool holder and tool holder to tool, that will actually create a judgment that how quickly or how accurately you are making a part which has a dimension in a tens of micron. So, let us see that what are the different type of retention systems, so that we can understand that which one is better for micro machining operation or micro machining tool. Right. So, this is the CAD, BT and ISO. This is very routinely used system which is a high steep taper and high speed spindle designed to use in the micro machining center must be able to automatically change the tool. So, that is mostly in happen because we many times we need a tool change because we want to create different type of dimension or different type of features onto the surface. So, mostly it is done by the CAD, BT and ISO. These are the three different standards by which it is defined, and these are the things because here we know that this is well known thing. So, there is a high steep taper. So, this is the thing, and then whole thing actually this whatever is there, your spindle is located at this location. So, it has also one taper. So, this taper in a tool holder taper is matching, and then it is actually pulling by a stud. So, this way you can get the insertion of this particular tool holder, and then tool is attached at this location. Okay. So, these are the CAD, BT and ISO type of standards. Right. So, it has a generally it is a taper is 7 by 24. So, what is that 7 by 24 taper? That suppose you have a length of a 24 inch. So, within the 24 inch whatever the taper is this taper is 7. So, now consider this L is 24, right. So, whatever taper you are getting here, so this is the taper. So, this taper is the 7. So, this is a 3.5 here, 3.5 here, correct. So, this is the taper. So, from this particular thing you can consider this is the part. So, this is the spindle, and total the length is the 24 and this is the 7. So, this is the 3.5, 3.5. So, depending on that you will get one angle, mostly this means this particular angle is something 8 point something is coming because this total angle is 16.23 or something is there. So, this is mostly you will get the angle is 8 degree or 8 degree and some point fraction of digit. So, this is called the 7 by 24 taper. Okay. So, taper tool holder establish their axial position in the spindle through the mating of two tapers. So, now we know that this is that one taper. So, on the top of that you spindle have one taper that is also exactly matching this part, otherwise you will get a wobbling within the system. So, this is the taper into the spindle, and then we have a knob here. This knob will be pulled inside and then these two surfaces will be in contact, and because of that contact you will get a friction here. This is a frictional joint, and then you this particular spindle whatever the RPM your spindle is rotating, the same way your cutting tool holder will also rotate. But this is mostly used for conventional thing, because when this thing was developed at that time there was no much boom or no much progress in the micro machining applications or machining at a micro scale. So, these particular standards are not actually designed with consideration of the micro machining part. So, we will discuss more about these particular things into the next class, that what are the other standards which are specifically used for machining of a micro machining part, and those standards, so that means that particular system will be used for a micro machining machine tool. So, that you will not get so much of problem, and those problems are actually associated with this CAD-BT ISO standard. Thank you very much.